Hey guys, welcome to another episode of Radical Dream Play. No, this is not a drunk person minding his own business driving down a road. This is, however, what our stock market does over several year periods. We can nicely see it follows a straight line, or it at least tries to. We can also see that it obeys some rules by staying on a straight channel that has an upper and a lower bound. And that is exactly why logarithmic plots, or more specifically here semi-log plots, are so invaluable to the financial industry. It is called semi-log since only the y-axis is scaled logarithmically. If both x and y axes were scaled logarithmically, then it would address power laws, like the relationship between the length of a side of a square versus the area of the square. But I only mentioned this to place the semi-log I'm talking about in context. So on the semi-log plot, finally trends can be seen. What would this look like if we used a linear plot? Well, with much more effort, we can still see the drunk guy making his way home. Sorry, I mean the stock market doing its thing. But now we have to zoom in and out and move the graph about, almost like the hokey pokey. With a semi-log plot, however, on the other hand, the values over 100 years can easily be seen on a single plot, but not so much on a linear plot. Try to read the historic value on these two plots. Which reads easier to you? And to think, this 100-year plot is barely scratching the surface of semi-log plots, since on the same semi-log plot, you can even represent both something the size of an atom as well as something the size of the whole observable universe. So we are not close to the limits of semi-log plots here. They can indeed be seen as limitless plots. A linear graph shows us differences. A logarithmic graph shows us ratios, which is ideal for exponential growth. And now, if you plot investment growth on a logarithmic y-axis, a constant percentage return becomes a straight line. The y-axis is all about the growth and the duration or the time. So here are the linear and logarithmic plots together. Both are correct, but sometimes changing the representation changes what you can see. On the linear graph, the later years dominate the picture. To just put the log scaling nicely into perspective, look at these three completely different growth rates: 5%, 10%, 15%. On a normal graph, they curve dramatically away from each other. On a logarithmic graph, they're all straight lines, and the difference between the growth rates appear as a difference in slope. The mathematics hasn't become simpler. The picture has become more informative, even from small values, without falling over at large values. Here's an exponential growth example. I'm using 10.4% growth every year in this example, something very similar to the stock market returns over extended periods. Let me plot this on a normal and semi-log plot side by side. Suddenly, the exponential growth becomes a straight line in semi-log. We have only changed the scale on the y-axis. Why does this happen? Because the logarithms undo exponentials. In investing, exponential means that our time variable is in the exponent. We can also call t times for how many times we repeat this returns. Taking the log function of a value really gives you the time variable as the output in fact. I want to explain two very important points of log functions using the following exponential equation. Firstly, let's undo the exponential by taking the logarithm of both sides. We get the log of the value equals t times the log of the returns, and the log of the returns is just a constant. So we have turned an exponential equation into a straight line equation like we have seen in the plots. Secondly, the returns can also be seen as the base value of a log. You can see the base as the step sizes. Take this exponential equation again and iron it out with a log function as follow from right to left. Then you get log with base returns of value is equal to the exponent, or the number of times you have to repeat the base to get to the argument value. And this is really the secret behind logarithmic plots. You can choose any base value you like to represent what you want using repetition. So with logs, we work directly with the multiplication of the base number with itself multiple times to get to the argument value. So next time you think about logarithms, think about them perhaps as different sizes base 3 logs that can be used as a measuring unit. See how I played with the words base and log there? Some wordplay, but I think there are some merit to think of it in this way. And this idea is actually more than 400 years old. In 1614, Scottish mathematician John Napier published his work on logarithms. And he wasn't trying to make pretty graphs. He was exactly trying to solve the painful problem of multiplication. Remember, this was before calculators, computers, spreadsheets, smartphones, and YouTube. If you were an astronomer and needed to multiply large numbers, you couldn't just reach for these tools in your pocket. You had to actually do the calculation. Napier's great insight was that logarithms could turn multiplication into addition, something humans are more comfortable with, and that was enormously useful. Henry Briggs took the idea further and introduced the base 10 logarithms. Henry also found long division, by the way, with common logarithms such that log of 10 is 1, log of 100 is 2, log of 1000 is 3. So multiplying by 10 simply meant moving one unit on the logarithmic scale. Think about how extraordinary that is to fit extremely vast ranges of values into a tighter representation. On an ordinary number line, just see how quickly small numbers get cramped up and immediately loses all value. From 100 to 1000 is 900 data points, and you can no longer sensibly see the value of 1 and 1000 together on one graph. But on a logarithmic number line, where every multiplication has the same amount of space, the cramping of values are more sensibly spread out, and the multiplication scale is thus used to represent vast values, rather than the standard addition scale we grew up with. And this is where logarithmic plots become incredibly useful in finances, particularly to the investing side. We use money every day with addition and subtraction, but we invest and borrow it with multiplication. So please, do not do your bookkeeping with logarithmic functions. Maybe only use log functions on your investments that adheres to equations such as the future value equation. This might be scary from a monetary point of view, but it is not fear-mongering. This is just me asking a simple question. Don't we perhaps plot things with unlimited size potential logarithmically? So what are other examples where we are using logarithmic scales? Well, earthquake magnitudes. The Richter scale is logarithmic because earthquake measurements span enormous ranges. Sound levels are another famous example. The faintest sound you can hear is over 1 trillion times smaller than a sound that will hurt your ears. Our senses are all logarithmic. In control design, we also work with decibels for gain plots. I'm just wondering, who ever used a sliding rule? This is a nice practical implementation of the relationship that logarithms bring to multiplication and addition. Thanks for watching another episode of Radical Dream Play. See you in the next one. I will be waiting. Cheers.